Assalamualaikum warahmatullahi wabarakatuh. So we are from group 10. Today we're gonna present about experiment 7. Our group consists of 3 members, which are Tariq Chogori and me, Muhammad Riaz, and Nozaldi Arki. For the first one, abstract. This experiment was carried out to validate Toricelli connection by comparing observed and theoretical velocity values. The apparatus of cylindrical cylinder with drill hole measuring tape and claymaker were used to conducting this experiment. Based on data collected, there are three different heights from floor surface to orifice are chosen, which are 36.65 cm, 56.45 cm, and 76.15 cm. Then we move to the second part, objective. The objective of this experiment is to verify Toricelli relationship by comparing measured and theoretical value of velocity. And then introduction. Toricelli's law, also known as Toricelli's theorem, is a theorem in fluid dynamics relating the speed of fluid flowing out of an orifice to the height of fluid above the opening, based on this formula. The law states that the speed of efflux of a fluid through a sharp-edged hole at the bottom of a tank filled to the depth is the same as the speed that a body would obtain by freely falling from a height, where g is the acceleration due to gravity. Toricelli's law describes the parting speed of a water jet based on the distance below the surface at which the jet begins, assuming that there is no air resistance, viscosity, or other obstacle for the fluid to flow. This experimental theory proves several such jets vertically aligned, leaving the reservoir horizontally.
Salam and good day. So I'm going to explain about the theory of experiment 7, Toricelli theorem. So for the theory, Toricelli theorem describes the relationship between velocity of non-viscous fluid flowing out from an orifice under the force of gravity and the height of the fluid, and then the speed v at which the liquid exits from the sharp edge hole, similar with the speed of a body falling from rest from the hedge. This one. And then for the formula of V is equal to root 2 times G times H. So this is the trajectory. For x direction, velocity of water can be obtained through the equation V equal to dx over dt equal to xb minus xa over tb minus ta for equation 2. And then since the water at initial ta is equal to 0, it is in stationary, hence ax equal to 0. So we get formula V mea equal to x root g over 2y for equation 3. And then for the y direction, this what? Assume free fall acceleration is constant over the range of motion and always direct downward. Effect of air friction, air traction is negligible. Y equal to yo plus vo times t plus 1 over 2 times gt square for equation 4. Since there is no vertical motion at initial state, therefore yo equal to 0, vo equal to 0. So for equation 5, y equal to 1 over 2 times g times t square. And then for equation 6, t equal to root 2y over g. And then for the methodology, step 1, the apparatus was set up based on the three different heights as shown in the figure. This one for the H1, height 1, and then this one is for height 2, and then for the height 3. For the step 2, the cylinder tank was filled with the desired volume of water and the hole at the cylinder tank was covered by using finger. For the step 3, the finger was removed from the hole. Step 4, the maximum water trajectory distance x reached by the water was marked by using clay and then measured. At the same time, the time taken for water to drain out was recorded. For the step 5, the experiment was repeated with different volume of water and different stake heights. Step 6, the result was recorded in table 1, table 2, and table 3.
Now moving on to the results section. So for this experiment, we were given a couple of parameters or a couple sets of data, as is demonstrated by the white columns. So we were given the height from the center of the orifice to the floor. We were also given the volume of water. We also we were also given the initial water level in units of meters. We were given that in terms of 3 experiments and an average was acquired. The same was done for the maximum water trajectory and the time taken for water to drain out. We were also given the water flow rate in units of meters cubed per second, and we were given the velocity of water. And now for the remaining four columns, we were the ones to generate that. The first one is the measured velocity of water using equation 2. This specific column was generated by dividing the maximum water trajectory distance by the time taken for water to drain out of the pipe or out of the tank. The second column is the theoretical velocity of water. We calculated that as well. The third column is the measured water velocity using equation 3. And then the final column is the error percentages. Now moving on to the discussion section. Dependent, independent, and constant variables. So in this experiment we dealt with three main types of variables: dependent variables, independent variables, and constant variables. Dependent variables are the variables that depend on other variables. Such variables that we dealt with in this experiment are the maximum water trajectory distance, the water flow rate, and the water velocity. Independent variables are variables that does not depend on other variables. So it's the opposite of dependent variables. Uh, such variables we dealt with in this experiment are the height from the orifice to the floor, the initial water level, the time taken to drain out, and the volume of water. And finally, we dealt with the constant variables. Constant variables are variables that are constant, that basically does not change regardless. So such variables we dealt with in this experiment are the gravitational acceleration constant g. Now moving on to the Bernoulli equation derivation. So to acquire the theoretical water velocity equation, we utilized to obtain the results of this experiment. We derived this equation from Bernoulli equation. So so we start by inspecting the image to the right. We disregard the tube to the right, and we disregard the open top and the orifice at the bottom left. So we implemented the Bernoulli equation for this image. So pressure at the top plus rho gh at the top plus half rho v squared at the top is equal to the pressure at the bottom plus rho gh at the bottom plus half rho v squared at the bottom. So h at the bottom was taken to be 0, and the velocity at the top was also estimated to be 0. So both variables were cancelled out. So so the remaining is pressure at the top plus rho gh at the top is equal to the pressure at the bottom plus half rho v squared at the bottom. Another cancellation that we did is that the pressure at the top and the pressure at the bottom, because both are equal to atmospheric pressure, because both are open. So what's remaining is rho gh at the top is equal to half rho v squared at the bottom. And we cancelled out the rows, so we got gh at the top is equal to half v squared at the bottom, and then we solve the equation for the velocity, and we got v at the bottom, or the velocity of water out of the orifice, is equal to the square root of 2 times the gravitational acceleration constant times the height of the water. Relative percentage error. So water velocity measured using equation 2 were close to the values provided. Theoretical water velocity was determined using equation 1. Water velocity measured using equation 3 was much closer to the theoretical values than that measured using equation 2. We can see from the following figure that the error percentages in table 1 were inversely proportional to the volume of water, whereas the error percentages in tables 2 and 3 were directly proportional to the volume of water. So sources of error in this experiment. So in this experiment, sources of error can be characterized into three main categories: instrumental errors, environmental errors, and human errors. So the instrumental errors include not adding enough water to the tank, corrosion of the tank, a crack in the tank causing leakage. The second type of errors is environmental errors. It includes platform shaking. It includes air breeze affecting the water trajectory distance. It also includes altitude. So altitudes can affect the atmospheric pressure. And finally, we have human errors. Human errors includes false reading of data and false estimation of data. So methods for minimizing errors. So it includes the following: ensuring that enough amount of water is added to the tank, ensuring that the tank is not corroded nor is susceptible for corrosion by adding anti-corrosive agents, ensuring that the tank does not have sources of leakage, ensuring that the platform is stable, maintaining an air-controlled environment, ensuring that the experiment is conducted at a reasonable altitude, and swapping manual means of reading and estimating data by digital ones.
Conclusion for the experiment 7, Toricelli can be used to demonstrate the relationship between the initial water level and velocity of water level from floor to orifice. Three different height from floor surface to orifice are chosen, which are 36.65 centimeter and then 56.45 centimeter, and then the last one 76.15 centimeter. The square of velocity of water is directly proportional to initial water level. The percentage error is also calculated by comparing the theoretical and experimental value. From the experiment, it can be summarized that the percentage error decreases with the increasing height from the surface to drill hole. So my comment is the percentage error of the experiment are relatively high due to the error done during the experiment.